In this video, I'm going to discuss a vertical asymptote of the rational functions. Asymptotes are just certain lines that tell us about the behavior of the function, how function behaves at the certain points. A vertical asymptotes show where the function has an infinite limit, unbounded y value. Based on this graph, we may notice two invisible lines, x equals to -3 and x equals to 1. And on both sides, function is approaching this line, but it's not touching. That's the basic general intuitive definition of the asymptote. That means function is approaching, which means it's getting unbounded y values, which means extremely big, infinity. Positive direction, positive infinity, negative direction on the left-hand side at -3, negative infinity. And on both sides at 1, we do have positive infinity. That means that's based on the graph, we may notice right away a vertical lines, which are the vertical asymptotes. However, we also have to know how to identify the vertical asymptotes based on the formula of the rational function. And this is the formula of this function. And we may notice that the vertical asymptotes actually are the lines, the numbers that are not in the domain of the function. Because we can see x cannot be -3 and x cannot be 1 based on the domain. And we do have an asymptote in these points. But we have to be really careful because the zeros from the denominator, the numbers that are not in the domain, they are only a potential candidates for the vertical asymptotes. In this case, we do have two zeros, -3 and 1, and both of them are the asymptotes. But this is not the case always. We have to do a few things, few algebra arithmetic things to decide whether all of the numbers, all of the zeros from the denominator will give me asymptotes or not. And let's see the steps. Having a rational function, the ratio of two polynomials, p of x divided by q of x. What we have to do, the first step is we have to factor out numerator and denominator completely. Then we have to identify any restriction in the domain of the function, which actually we can even do this first. We can do any restriction, which means we have to eliminate all of the zeros from the denominator. I mean, that's how we can identify the domain. But now, reduce the expression by canceling the common factors in the numerator and denominator. That means factoring out and canceling the common factors will give us a simplified version of the rational function. And then all of the zeros from the denominator will give me the vertical asymptotes, only from the simplified form. Also, we have to note that any restriction in the domain where the asymptotes do not occur, this will be removable discontinuity. And let's apply this to our examples. Find all vertical asymptotes of the following function. Rational function x plus 8 over the quantity x minus 4. That means what we can see. We can see right away that 4 is not in the domain. That means this is important to notice. But do not assume right away that this will be an asymptote. We have to check few things. And actually looking at this function, this is the first degree polynomial. This is also the first degree polynomial. Is the linear factors. They are not the same. I can't factor out further and I can't simplify because they are not the same. That means this is the simplest, that's the simplest reduced, I can say, form of my function. That means, yes, this will be an asymptote, a vertical asymptote, okay? Because I can't simplify. And what I can do, I can try to draw this function, line, invisible line, 4, it's gonna be my asymptote, vertical asymptote, and I can possibly draw a function, okay? And what I can do, one thing that is really helpful, I can add a little bit of calculus. Since number 4 is not in the domain, I can investigate how function behaves on the right and on the left-hand side, which means I will compute a limit as x goes to the 4 from the left-hand side. Okay. Of course, it must be unbounded y value, infinity. But let's check if this will be positive infinity, the function will go up, I mean on the left-hand side, up or down. Okay, 4 from the left, 4 plus 8 will give me positive number, 12, but 4 minus 4 will give me 0. But since this is on the left-hand side, is 3.9. 3.9 minus 4 will be a small negative number. That means 12 over small negative number will give me big negative number. That means function will go actually down, negative infinity. And I'm assuming, since everything sounds so simple, on the right hand side, the limit is still positive, but this will be like 4.1, 4.1 minus 4 is positive number, positive infinity. That means function will go up, right? Positive infinity. Okay? That's how we can draw, but definitely line 4, it's a vertical asymptote. That we can see, we can answer this question quite quickly, just having an answer, whatever was asked, the asymptote, but we can always have a proof, the calculus proof, that we have unbounded y value, infinity, on both sides. In this case, okay, example number 2. Find all vertical asymptotes of the following function. Okay, we do have function x squared minus 9 over x minus 3. That means I can see right away that the value 3 is not in the domain of the function. But please do not assume that this is a vertical asymptote. We have to simplify a function, and quadratic expression, I can x squared minus 9, I can factor out as a x minus 3, x plus 3. And now what I see a common factor. That means in this case, I have to simplify, and my function in the reduced form has a formula x plus 3. No zeros, no denominator, no zeros in the denominator. That's when I think this function doesn't have a vertical asymptote. No vertical asymptotes. And what is the graph of the function? We can also draw it. I did reduce the function to the linear function x plus 3. Function x plus 3 looks like that. Y-intercept 3, x-intercept negative 3. But what is important, this is still not the correct graph. This function, this line is not defined at 3. That means for x3, I have no value. I can draw it again. The function will have, the point is removed. It's not an asymptote, but the value is removed. And we can easily find this value, computing. We can easily find what is the level, the height of this open dot, this removed point. It's removable discontinuity. Computing a limit as x goes to 3 of function. But I know that I can simplify the function to the form x plus 3. That means function, my original function, or the reduced form x plus 3 at 3 behaves 3 plus 3 is 6. That means this value is 6, but it's not, it's just the limit, the behavior of the function near 3. That means I'm adding a little bit of calculus, but I'm also answering the main question. Vertical asymptotes for this function, they do not exist. Okay, example number 3. Find all vertical asymptotes of the following function. Rational function x minus 3 over x squared plus x minus 12. That means I see linear term on the top, nothing to do, but in the denominator I have quadratic function, and I believe we can simplify, we can factor out. It will be 3 and 4, negative, positive, because negative 12 and positive 1. Okay, and again, looking at the function, I see that x3 is not in the domain and x negative 4 is not in the domain. However, do not assume that both of them will give me a vertical asymptote. I also see a common factor. I can cancel out. That means the reduced form of my function is 1 over x plus 4. That means since I reduced, this will be no vertical asymptotes at this point, but this will be a vertical asymptote. That means we do have a vertical asymptote at negative 4. This is a vertical asymptote. And we can also draw a function. This is a vertical asymptote. I can draw actually invisible line. Negative 4 is my asymptote. And function behaves, again, trying to check how function behaves at negative 4 from the left and from the right hand side. We have to find a limit. That means let's try how function behaves from the left hand side. 1 over x plus 4. That means this is 1. 4, it's negative 4. Limit, negative 4 from the left hand side. Negative 4 plus 4 is 0, but negative 4 from the left hand side is negative 4.1. Plus 4 will give me negative number. 1 over small negative number is giving me big negative number. That means function is going down, negative infinity. And of course, since this is simple form, behavior from negative 4 from the right hand side, the little plus represents the right hand side of the form 1 over x plus 4 will give me negative 4 plus 4, 0, but negative 4 from the right hand side is like negative 3.9. Plus 4, it's positive number. That means 1 over small positive is the positive big. I mean, function will go up, positive infinity. We also have to note that x equals to 3 were not in the domain. Okay, that means we have to know that the function doesn't have a value at this point. I can draw it. We will have a removed point. And we can easily find the value because I can compute a limit of the function with the reduced form 1 over x plus 4 as x approaches 3. Substituting 3 plus 4, 7, 1 over 7. That means this is 1 over 7. The limit, the behavior of the function at 3. We can also find y-intercept. Y-intercept means the x is 0. If I substitute 0, 0, 0, negative 3 over negative 12, it's a quarter. Just if we... Also, in these cases, I'm not discussing a horizontal asymptote, but I will discuss this in my next video. Only the vertical asymptotes. That means we can see the blue numbers are my answer. X equals to negative 4 is the vertical asymptote only, not 3. Example number 4. Find all vertical asymptotes of the following function. X minus 2 over 5x squared minus 20x. Looking at the zeros from the denominator, I will factor out first. Nothing to do on the top, but I can see 5x being a common factor. X minus 4 stays. Okay, that means now I can see 5x will give me 0. 0 is not in the domain, and 4 is not in the domain. And what I notice that I don't have a factor x, and I don't have a factor x minus 4 on the top. That means this is, I did factor out, but this is my simplest form of the function. Nothing to be cancelled out. That means probably the vertical asymptotes are 0 and 4. I can still compute a limit and prove this, that we have unbounded y value. However, I can't cancel out. These are the vertical asymptotes. If we would like to get the answer right away, vertical asymptote at 0, vertical asymptote at 4. And it's not, we still need a few things to, I can try to draw a function y and x just to show the asymptotes. 0 is actually the y axis, and 4 will be here. And again, computing a limit, I will find out how function behaves. Let's try limit as x goes to 0 from the left-hand side. Function is x minus 2, 5x, x minus 4. That means 0 will give me negative 2, 0, it's a little bit less than 0. That means this will be 5 times 0 will give me 0 but negative, and negative number and negative 4 will also give me like negative 4, small number. That means what I have, I do have a number over 0, over small number. I will have big number, but let's investigate. Negative, negative, and negative. Multiplying 3 times negative, I'm still getting negative. That means function is going down. Negative infinity. Okay, and on the right hand side, probably this is the right hand side, x minus 2, 5x, x minus 4. This will give me negative again. This will be positive 0, because on the right hand side at 0 we have positive number, and 0 minus 4, it's still negative. Dividing by small number, dividing by almost 0, we're getting big number, but now it's negative over negative is positive, and another positive. That means function will go up. And this is the y value, and function will go up. Another thing, I can find I can see that x-intercept is 2, because I can just solve the top. And I'm just assuming that function will behave like that. This is 2, function will go. On the left-hand side at 4 will be negative infinity, and on the right-hand side will be positive infinity. I can, of course, prove this. Let's compute limit as x goes to 4 from the left-hand side, x minus 2, 5x, x minus 4. 4 minus 2 is 2, positive. 5 times 4 is 20, but I can put actually positive, because I'm only looking if it's positive or negative. And 4 minus 4 is 0. But on the left-hand side, I do have a value 3.9. 3.9 minus 4 is negative. That means positive 2, positive 20, but negative 0 will give me negative infinity. And we can see negative infinity. And on the right-hand side, x approaches 4 from the right-hand side, x minus 2, 5x, x minus 4 will give me 2, positive 20. 4 from the right-hand side is like 4.1, minus 4 will give me 0, but positive. And this will be positive infinity, and it is positive infinity, also this one. That we do have a nice rational function, and my example is, of course, showing you, my point is to showing you that in this case, we didn't simplify at all, and we do have 2 vertical asymptotes. That means theoretically, to answer this question, you can just look at the blue notation, 0 and 4 right away, because we not simplified. And this is a little bit of calculus if we need to draw a function. Okay, I have another one. Find all vertical asymptotes of the following function. Okay, that's me. Now this one, let's simplify. Because we have x squared minus 1 quadratic expression, I think I can factor out as a x minus 1, x plus 1, and then denominator I can factor out as a x minus 1, x minus 3, however x plus 1. Because this is negative 3 and negative 2. Okay, that means what I see, first of all, I see that x negative 1 and x positive 3 is not in the domain. But we just learned that we can't assume that both of the numbers will give me a vertical asymptote. I can simplify. I am simplifying this way, and my reduced form looks like x minus 1 over x minus 3. That means x equals to negative 1. It's not a vertical asymptote. No vertical asymptote because it's reduced. Will be removable discontinuity. But this one stays. This is a vertical asymptote. Okay? And again, we can try to draw it. We do have a vertical asymptote at 3. Okay? And you can try to get, I can draw on the left hand, on the right hand side function will go up, and on the left hand side function will actually go down. And we do have a y, x and y intersect. X intersect is, we can say it's 1, and the y intercept means that x is 0. That means negative 1 over negative 3, it's 1/3. That means this will be 1/3. And also for negative 1, we do not have the value. I can draw an open circle, and I can simply compute that behavior, how function behaves at negative 1. X minus 1, x minus 3. Direct substitution will tell me negative 1 minus 1, negative 1 minus 3. Negative 2 over negative 4, it's simply half. That means that this is the value 1/3, but this dot is 1/2. Okay? And you can check the limits at 3 from the left and the right hand side. But the answer for this one is again only 3, x equals to 3 is an asymptote. And I have one more. Find all vertical asymptotes for the following function, sine of x over x. Okay, that means this one we can definitely see that x0 is not in the domain because it's sitting in the denominator. And thinking about simplified, okay, of course I can't simplify. Right? I can't simplify this function because sine of x over x, I can't really simplify. That's me what you can probably, like what kind of conclusion you can make. You can probably make the conclusion that, well, that means this is a vertical asymptote. That's the 0 from the denominator, and I can't simplify. But we still have to be really careful because this function is not a typical rational function. It is the ratio, but it's not really the ratio of two polynomials. That means even if that 0 is not in the domain, I will still compute a limit at 0 of this function. That means how this function behaves at 0. And we recognize this limit, sine of x over x at 0 is 1. That means this limit is not infinity. The values are approaching 1, not unbounded, not infinity. That means this is definitely at 0, we do not have no vertical asymptotes at 0. And I can sketch the graph. We don't really have to, that's actually x. The graph behaves a little bit like that. And that means we can see at 0, it's 1. It's definitely not a dotted line. That means please be really careful, especially for a little bit different type of the rational function, which this is the ratio of not of two polynomials. Okay. Thank you, and I hope you understand the vertical asymptotes concept now.